Hi everyone. Welcome to this supplementary video. This video is related to the topic of lubrication flows or nearly unidirectional flows. And in the class, we had discussed about how to solve these problems, in which basically we start by solving using the lubrication equation. And the specific problem was on the ball bearing slipping on a surface. The surface is moving at a velocity u, and there is some sort of a lubricant that is filled between the ball bearing and um, the plate. And if the plate is moving at the velocity u, and then ball bearing has this y equal to h of x curve that defines the system. So we had discussed that you can essentially directly use the governing equation, and the governing equations are del p dp by dx is equal to mu del square vx by del y square. And remember, we had discussed that it's a thin problem, so h by l is small, and Reynolds number times h by l is also small, so we can use the lubrication flow problem. So pressure is only a function of x, and we have vx being function of both x and y. So that's why you have a del square vx by del y square, and so on. And once you have all of this, then you also use continuity equation to find the invariant. And invariant in this case was flow rate per unit width, which was small q, which is what we used to close out the system. So you integrated the equation, and then we found this result. Okay. So you can find Vx and Vy, and we basically left at the point that we did not calculate forces in the system, and I just want to kind of go through them once to make sure that you are able to see how to calculate forces in the system. And by the way, this will help you with homework 2, problem 2, the air hockey problem. That is actually a lubrication problem. You will find there VR and VZ, and then at the end of the day, you have to find the force keeping the air hockey puck afloat. And so that's why, like, you want to make sure that you kind of understand how to calculate forces. So this is essentially what we have done. And you go from here and you use invariant to find these equations. And invariant is used by continuity. All right. So now let's quickly discuss how to think about the force on the ball bearing applied by the fluid, and it's a stress vector. So stress vector is n dot sigma. And we had studied this in class. We had mentioned this n vector comes out to be actually dh by dx ex minus ey, and we use the minus ey. So there's the plus minus, but we focus on the minus ey because normal vector points into the fluid, and then we get 1 plus dh by dx whole square. So we had discussed this, and we said we can approximate this as dh by dx ex minus ey. So this is something we had discussed in the class. And what we had essentially left is how to calculate the stress tensor sigma. So stress tensor sigma. Okay. So remember, stress tensor sigma is minus pi plus tau is equal to minus p plus tau xx, tau xy, tau yx, or rather, it's the same thing. Both of them are same, and minus tp plus tau yy. Right. So this is what we have. Now at this point, please make sure that you remember that you have to invoke order of magnitude analysis. You could essentially, in principle, actually solve the full problem, but I would highly advise against it. Please don't do that because it takes a lot of time. And although you can solve it, it's just not worth it. It's just much easier to solve the problem using an order of magnitude analysis when it comes to force balance at this point. Okay. So this last step, when you're calculating force balance, you go and you essentially look in the table, which is what I'm doing right now as I'm recording the video. I'll show you what the table is. It's table 6-4. We have mentioned this in class. Here we'll see what tau xx is. So tau xx is 2 mu vx, 2 mu del vx by del x. Tau xy is equal to tau yx is equal to mu del vx by del x. So del vx by del y plus del vy by del x by del x, and tau yy is mu 2 mu del vy by del y. Okay. And remember that we had also calculated pressure. So I will discuss it in 1 second. Okay, so you have these terms. Let's try to do an order magnitude analysis. So this is 2 mu velocity in the x direction. So how do I think about velocity in the x direction? The simplest scale is, well, velocity will have some scale as its slip. Okay, that's the simplest scale. You can think the velocity will have a scale as a slip. So 2 mu u by L. Okay, and then tau yy is 2 mu v y by h. Okay, so this is my vy, which is the velocity in the y direction. Velocity in the x direction is simply u. Okay, but how do I think about the scale of this? Is that, remember, we also have continuity. Continuity also requires us to say del vx by del x plus del vy by del y is equal to 0, or this means that u by L is similar to vy by h. So I can also write this as 2 mu u by L. So it's just the same thing, because all the other way to think is this is del vx by del x, this is del vy by del y, and they are equal and opposite in terms of magnitude. So it's just 2 mu u by L. Okay. Now what we do not know is the pressure. So how to think about the pressure? And in the actual problem, you do calculate pressure. You can calculate pressure, but I just want to show you how you can also estimate pressure using directly the equation. Remember, our equation is this. Okay. And so the pressure, I'll just write it here again. So del p by del x, sorry, dp by dx. So this is our governing equation. Okay. So you can calculate directly. I'm not trying to tell you to not calculate pressure, but I'm just trying to show you how we can also use scaling analysis to make that inference. Is del dp by dx is equal to mu del square v x by del y square. Okay. So we have this. So this means that we have pressure by L scales as mu u by h square. Okay. So we get this, or we basically get mu u by L times L square by h square. So this is what I get as pressure. Okay. Now the reason to do this is that note that my pressure has a scale of mu u by L, and then I have this L square by h square here, L square by h square. And here I just have mu u by L, and the two factors don't matter in order magnitude analysis. So remember that the factors of 2 or 3 don't matter in order magnitude analysis. So clearly my pressure is greater than tau xx, which is similar to tau yy, right? So pressure is much bigger than these two terms. So from that perspective, I can simply remove this term here. And whenever you see two terms, try to use order magnitude analysis, and we basically don't have to calculate del vx by del x, del vy by del y. Just easier to just see this and just say pressure is the only term in these two diagonal terms. That's important. Now tau xy and tau yx, we have still not done order magnitude analysis, and we can see that this is equal to mu u by h plus vy by L. Okay, so this scale is vy by L, this scale is u by h, right? And I can say this will be mu u by h, and remember that this is actually u times h by L from this formula here, from continuity. The right hand side here is u h by L. So remember, vy is u h by L. Look at the left hand side, the red circle here. And so when you take u by h outside, you will get 1 plus h square by L square, which means this term is very small. And really it is the del vx by del y term that dominates. So this is much greater than the second term here. Okay. So always make sure when you're neglecting h by L, it is next to a 1. Okay, that's important. And so you get a term of mu u by h. And basically that's the term which we will use here. So in simple terms, my sigma in that way becomes minus p mu del vx by del y, mu del vx by del y. Yeah, this is my sigma. Right? This is very important. Now, at this point, I want to emphasize a common mistake that students do is that we have scaled pressure. We have said pressure is mu u by L into L square by h square, or we can say pressure is mu u by h, right? Okay, I can just like write this times L by h. We can also write it just like in terms of mu u by h. And this scale we said was mu u by h. Okay. So students say, well, pressure is also much greater than mu del Vx by del y. So they just remove this term. They say this term does not matter. And this is a common mistake. Please don't do this mistake, because remember, I want to emphasize that you cannot just ignore something which is not added to something else. So whenever I've ignored everything, note that I've ignored it when this term was much smaller. So this blue term here, I'm shading it now, Vy by L. This is much smaller than U by H. That's why I ignored it. That's why I ignored the del Vy by del X term. Similarly, I ignored the tau XX and tau YY when it was next to P. So please don't just ignore any term. It is small, but it will be small compared to something. So you can only ignore the term when it's actually added to something, rather than you cannot just directly ignore anything that looks small without any having a big term next to it. So please don't ignore it. Okay. So I will just remove this and say this. Don't ignore this. Just arbitrarily, it should be next to something to be ignored. All right. So this is the way you found stress tensor. This is how you should do it in your air hockey problem as well. And then you go further and you go say stress tensor Sn is dH by dx Ex minus Ey. This is your, or rather -1 in terms of matrix. This is your n dotted with minus p. This term is your n. And then this is here mu del Vx by del y, mu del Vx by del y minus p. Okay. And this is your sigma. Right. So now if you do this further, then you will get Sn. You will get dH by dx minus p, dH by dx minus mu del Vx by del y is Ex. Then we'll have plus dH by dx times mu del Vx by del y plus p Ui. Okay, so you can just do the matrix multiplication, and this is what you get. Now again, I have several terms in the system. I have Ex and Ey. Note that I cannot compare any Ex and Ey. Ex and Ey are different directions. So I can only compare these two terms and these two terms. Okay. Now I have scales for each of them. So the scale for mu del Vx by del y is mu u by h. Scale for pressure was mu u by h into L by h. And dH by dx is h by L. So you can see that these two terms have similar scales. I cannot ignore any of them. And this is where I want to emphasize. I had mentioned this in the class also, that see, the pressure does not only contribute to the normal force. Because of the dH by dx, pressure is also contributing to the parallel force. It's very interesting that pressure actually also ends up impacting the x direction force. Now, let's go to the normal side. We have h by L and mu u by h, and then pressure is mu u by h times L by h. So essentially, clearly, this is much smaller because this is h by L and here it's L by h. So I can ignore this part. And the shear stress, although does contribute to the Ey, it's very small and not comparable. But in the parallel plane, you actually do have Sn contributing to both. So basically, finally, I will have force as minus p dH by dx minus mu del Vx by del y Ex ds. And I have not discussed ds yet, plus p ds dy. P es dy. All right, so this is your full solution. Let me just make sure my signs and everything are correct. They are fine. So this is at the, and just note that this will all be calculated at y equal to h of x, which is obvious here at the surface. I mean, it doesn't matter. P is only a function of x, actually. P is only a function of x. All right. So there will be both x component and the y component, and you can calculate them. The small thing I just want to mention is this ds. This is an odd geometry. So whenever you see an odd geometry like this, it's a little difficult sometimes to understand what this ds will be. But I hope you can see this will be something like this. And then in the z direction, you will have like a strip like this. So you can essentially say it will be something, some width w times this distance. This is, and if I zoom in here, it's dx and dh. And so this will be dh square plus dx square. So your area becomes w times square root of dh square plus dx square, and w times dx into 1 plus dh square plus dx by dx square. This is not the right order, right? Dh by dx whole square. And this is simply w dx because dh by dx is very small. So it is simply dx. So this becomes w dx, but it is the way you can see that it is, it comes out to be through some sort of geometry. You can show that it's dh by dx, but if it's a more complex geometry, you may have to adjust it, but we will not do that in the class. But I just wanted to kind of show you how to think about the area, differential area elements. For other geometries like Cartesian, cylindrical, and spherical, you can just look it up in the appendix in the book. Okay. So let me just emphasize once more how we solve the full problem. So we said, well, in the class, we derived the velocity profiles. We had the pressure equation, which is dp by dx is equal to mu del square v del y square, or the lubrication equation, and the continuity equation. We use that to calculate using invariant velocity profiles. Then we started with stress vectors. For that, we first found the normal into the fluid. Then we wrote the stress vectors, the components of the stress tensor down, and showed one by one how pressure dominates in the normal direction, and mu del bx by del y dominates in the off diagonal terms. Then when we took the Sn n dot sigma, then we found the two terms in Ex and Ey. Pressure contributes in both Ex and Ey, and shear stress contributes in both Ex and Ey. When we calculated order of magnitude, we found in the left hand Ex term, P dh by dx and mu del Ex by del y to be similar. So we cannot ignore any of them term. And the right hand side, in the normal direction, it's only the pressure. Okay. So in our air hockey problem, you will do something similar. You will get both of these sort of terms in one in Ex and one in the radial and the z direction, and you will integrate out them and find a solution. We will not do this because this is a very general problem right now. You need the profile of h of x and so on to find, but in an air hockey problem, you will be able to do that. Okay. So hopefully this video was helpful. I look forward to seeing you in the next video.